me?
Yes.
Okay, beware, we're being
Yes.
recorded from now. Does anybody have any sense if we should be expecting any further participants, people to join in? Or
People
should
are-
we start?
People are still joining in. If you wouldn't mind giving it 1 more minute.
No trouble at all.
Okay.
Well, I'm Ben Dyer. I'm Ben Dyer. I'm from Geo-Energie Suisse, and I'm going to be presenting today with my colleague Falko. So first of all, welcome everybody to the modeling forum, and thanks very much for joining the meeting today. I think probably also want to offer some thanks to Gosia and Rob for organizing the meeting and inviting us to make the presentation today. Can I just check, can everybody hear me all right? Are we clear enough?
Your voice is a little spotty, but I think we'll be okay.
I think we're all right. I'll come a little closer to the screen then. Right, at this point, I've got to try and share my screen and let you see the presentation. So here we go, share the screen. Let's click on that. Okay, and then slideshow from the beginning. Okay, can everybody see the first slide?
Yes.
Great, thank you. Okay, so the title of the presentation today from myself and Falko, Microseismic Monitoring and the Risk Mitigation Plan for the first Utah Forge stimulations that will be at the toe of 16A 32. We'll just begin by introducing or reintroducing the authors who've been working on this, the little group of us. And so from Forge, the University of Utah's Chris Pankow, and she's the sort of overall seismic monitoring coordinator. Chris also looks after the surface seismic monitoring networks, which I won't be discussing today at all. We're just going to be looking at the deep downhole monitoring networks. Also, Joe Moore is the principal investigator, and Joe keeps us up to date with all the drilling schedules and the logging work and all the practical activities on site. There's Phil Wanamaker, who's looking after resource characterization and is also heavily involved in the downhole monitoring design. Jim Rutledge is working as consultant to the University of Utah group. He's worked for many years in oil field frac monitoring, and I think it's fair to describe him as an expert in this field. From Geo-Energie Suisse, there's my colleague Falko Bethmann, who will be coming on after me and discussing the risk mitigation and the ATLS work. I'm going to be discussing network modeling and monitoring system. And then we have Peter Mayer, who's the CEO of Geo-Energie Suisse and the hydraulic specialist. So here's the abstract. I've just included this well, to be complete, but I'm not going to read all of that to you. So first off, just to say a few words about the role of Geo-Energie Suisse and why we're involved at Forge. We're participating through a program called IAS, which stands for Innovative Acquisition Systems and Software for Deep Geothermal Evaluation and Monitoring. So the aim of IAS is to identify and validate through field trials proven microseismic monitoring and processing system. The Deep EGS project, which is a project of Geo-Energie Suisse at Haute-Saône in Switzerland. So IAS is a Swiss project to test and validate innovative acquisition systems and imaging techniques. And these are aiming at minimizing the seismic risk of deep geothermal projects And this really is an essential element of the overall intention to have this deep project at Haute Saône. So this IAS is a critical element of the project. I've got something going bing bong here. I'm not sure why, but hopefully
people are muting it because people are joining the meeting.
Okay.
Just ignore it. You are the co-host and you'll be hearing beeps. Just keep on going.
All right, thank you for that. Thank you. Okay, so the two principal sort of field aspects to IAS. First off is some low temperature sort of tool selection and pre-qualification seismic tool performance testing. So this is work that we've been conducting at Pedretto Underground Lab in Switzerland. So we've already commenced that work. We had 2 field campaigns, firstly in the autumn last year, and then again in April, May this year. So there we've been looking at different geophones, tool systems, and so on. And second, and really very importantly for us, is participation in the Forge program. And this is an essential part of IAS to enable us to perform high temperature downhole testing and validation of real-time microseismic processing and risk mitigation methods. So Forge is really a very important part of this IAS program. So to date, the sort of contributions of GES to Forge have been resolution and sensitivity modeling. We will provide 2 high temperature 3-component strings for the stimulation, which is currently scheduled for sort of November, December this year. We're also going to provide real-time monitoring and preliminary microseismic event locations and magnitudes, and this will feed into a TLS, ATLS type seismic risk mitigation scheme. So let's have a look at the Forge site. This is obviously a slide people will be familiar with. So here we've got in yellow dotted dashed lines the new deep stimulation hole 16A, and the first stimulations will be down here around the toe of this well. So it should be 2 or 3 intervals to be stimulated. The older monitoring well here is 5832, which is called the pilot well up here on this plan. There's also a rather shallow sort of monitoring well, 7832, which is about sort of 3,280 feet. And we'll use this well for testing some innovative tools, not for the main part of the monitoring. And over the last year or so, a second monitoring well was first drilled here at 5632. This is actually rather deeper than this diagram shows. It's 9,135 feet. And lastly, a third deep monitoring well has been drilled off this pad at 7832, and that's at about 9,500 feet. So the microseismic data processing, the acquisition cabin is going to be here on this pad at 7832. And we'll collect there the data from the monitoring in 5832 and 5632, and also the rather nearby 7832 well, which is called 7832B for the deep well. So the overall aims of the modeling that I'm going to talk about then is really to identify the optimum network for monitoring the stimulation here at the toe of 16A. So here's 16A again. So we're looking to have good resolution and sensitivity in this region here at the toe of 16A. This process of modeling has gone through a number of iterations, and part of the reason for that has been that we've needed to identify best positions we could find for the new monitoring wells here at 5632 and again at 7832B. They were always going to be roughly in these positions, but there's certain sort of practical considerations as to where they can be and cannot be. And so we performed a number of modeling iterations to help resolve that. So we looked at the sort of number of sensors and the depths and the spacings for the sensors within each hole. And from the sort of final choice of these two new holes and the existing hole at 5832. I'm going to show you today the sort of relative location accuracy we can expect and the sensitivity of the network. So what are the objectives of this deep microseismic monitoring? What we're looking to do is to provide real-time locations and magnitudes throughout the stimulation of 16A32. So this is the stimulation at the toe of the well, and also real-time TLS and ATLF. This is the adaptive traffic light system, the seismic risk mitigation. And then following the stimulation, the monitoring network will change, and we will install a slightly different network for long-term monitoring and background monitoring. And lastly, we want to test some innovative tools, and this testing will take place in the 7832 well, which is the rather shallower monitoring well. So the way we've gone about this is that over the last year or so, we've had a weekly technical planning meeting together. So myself, my colleagues from GES, and the colleagues from Forge, and Jim Rutledge as well taking part. And so we've looked at the locations for the two new monitor holes, microseismic network design. We've looked at selection of tools, and wire lines, site services and access. Data networks are important because we're trying to link together a number of different acquisition systems and some quite high data rates. And we've also been looking at where we're going to place check shots and vibes for velocity evaluation and for orienting the geophones as well. And secondly, over the last few months, we've had a weekly meeting on a sort of ad hoc basis with the wireline service provider, which is now going to be Schlumberger. So here we've got a plan view, is shown in 3D, of the networks that we're proposing or planning to install. In red here is the stimulation well, 16A32. And the primary network, as I've been referring to it, consists of 3 8-level geophone strings. And so these strings are going to be installed in 5832, 5632, and 7832B. So these networks, these strings will be installed to monitor the stimulation. And then after the stimulation is complete, the 3 strings will be removed and will be replaced by 2-level strings shown here by the green spheres. And these will be installed for the longer term to perform background monitoring. And thirdly, we've got some innovative systems that we're going to deploy. And these are going to be in 7832, here, the more shallow well. These two wells actually are very close together, about 30 feet apart. So they look as though they're on top of each other in this diagram. So what we have in 7832 is a fiber optic 3-component string. So this is a 3-level string, and each level is a 3-component fiber optic sensor. So this is referred to as BOS, Boral Optical Seismic System, I think. And also with that system, there is DAS in the wire line. So this is quite interesting for us because in the 7832 well and the adjacent 7832B well, there is DAS fermented behind the casing. So this gives us an opportunity to compare DAS in the wire line with behind the casing DAS. The other innovative system that we will have will be the placement here of this deep string. As you go to the east at Forge, the temperature gets hotter. And so whereas these two strings, 58 and 56, will be deployed to sort of 195 centigrade, this string here in 7832B will see higher temperatures. And so that's another innovation. So here is the string we're proposing to use. It's an 8-level string from Avalon. this is a very well established three-component geophone string for VSP and microseismic monitoring. So it's got proven reliability for oil field applications, and the string is it's a digital three-component string. It's got high sensitivity, and at the present time, it's probably got the highest temperature spec of the strings that are available. A particular and unique feature of the Avalon system is that they have an active cooling function, and this keeps the internal temperature of each of the geophone sondes at less than 165 centigrade. And this is a very important function because it keeps the electronics cool and enhances the reliability and longevity of the electronics. The tools also have a motorized clamping arm. You can see that just here. And within each tool, there's temperature monitoring. So with these arms being motorized, if the tools start to reach their maximum temperature, 165 centigrade internally, then we can withdraw the arms and move the tool to a lower position within the hole to cool down. They also have another unique feature, which is what they call a high side indicator. Now, this is an accelerometer which measures the relative bearing of the geophone group within each tool. In this instance, we will also orient the tools either with a check shot or with a check shot and with vibes on the surface. And this sounds like belt braces, but in fact, the high side indicator is less accurate in near vertical holes. So it's important to have this backup from the vibes and a check shot. So the general spec for these tools, they'll have 8 levels. They're going to be 100-foot intervals. The maximum temperature limit at the moment is 210 or 215 centigrade, something like that. So this is with the enhanced function that they've been working on over the last year or so to increase the capacity of the active cooling so that it can handle higher temperature boreholes. They have 3-component fixed cartridges, which is fairly standard for microseismic monitoring, and just the latest sort of 24-bit sort of standard for analog to digital conversion and quarter millisecond sampling that you sort of expect from these tools. The tool is going to be deployed on standard 7-conductor high temperature wireline by Avalon, ASL as it's called here, and by Shear. So I say these tools are going to be deployed at depths really constrained by the temperature in the boreholes. And so in the 2 western boreholes, 58, 32, and 56, 32, they'll be deployed so the bottom tool is at a temperature of around 190, 195 centigrade, something like that. So this is the maximum temperature of the standard tool. In 7832B, you can see it's actually the tool string here, the red arrows means that it'll actually be slightly shallower, and that's because the temperature increases as you go to the east. And this tool will be at a maximum temperature of 210 to 215 centigrade. So that's this dotted line here. So now just get on to talking about the resolution modeling. So I'm going to talk first about the primary network modeling. So that's the network of our 3 8-level tools. So for the modeling, we're going to look at the overall sort of worst case resolution. So this is the resolution in any direction. You can also look at the horizontal or the vertical resolution separately, but I'm going to show you is the worst case. So what we're going to model then is our 3 8-level strings, and the model data will be the constant P and S wave velocities, picking accuracies for the modeling around plus or minus 1 millisecond for the P and plus or minus 2 milliseconds for the S wave. These are sort of typical values that we see for similar monitoring operations. And for the modeling, we'll use P and S picks for all the groups. So that'll be 24 in all, so 8 levels in each string. I haven't included hodograms in the modeling because we actually expect not to need hodograms to locate the events in this application, because we've got the three borehole strings in a sort of triangular configuration. However, if we do get problems with any of the strings, we may need to use hodograms, which is why we will orient the tools and have the facilities to locate with hodograms if necessary. So here are the velocity logs, and I say the modeling is being performed with constant P and S velocities. As you can see here is the P velocity here in the granite. It's pretty constant, and again for the shear wave velocity. And we can use a constant velocity because the sensor strings and the stimulation zone are all within the granite. So we're not expecting to have to model velocities anywhere else. So just a few sort of general comments about how the resolution modeling works. It's actually relative event location accuracy that's being modeled. I've rotated the coordinates about 15 degrees anti-clockwise, and this is basically to put the stimulation hole 16A32 sort of normally west to east. It just makes it a little easier to see what's going on. So we calculate the resolution on west, east, south, north vertical planes and a horizontal plane. So I say at each grid point we can evaluate the horizontal resolution, the vertical resolution, and the overall resolution in any direction. And I'm going to show you the overall resolution. And we find this by conducting a stepwise search, moving out at increments of 1 foot at a time from the grid point on our image planes, searching for the furthest offset we can find that fits within our data accuracies of plus or minus a millisecond. So here are the resolutions that we found. So this is for the primary network for these three 8-level strings shown here, 58, 56, and 78, 32 here. It's showing us that in the toe region here of the stimulation hole, we can expect resolutions of say 50 to 60 feet. And this is a vertical section through or along the stimulation hole. And then here is the top right is a horizontal section, and this is a horizontal section at 8,500 feet, which goes through the toe of the stimulation hole. So what we see is that for these three geophone strings in this network, the primary network, we get quite a nice, consistent, gradual change in the resolution. So no nasty holes or anything. So this is going to provide us with pretty good resolution for fracture mapping and correlation with borehole logs. But just to emphasize this, those relative resolution, it's the resolution of one event with respect to another. It's not the absolute resolution. As I'm sure everybody will realize, that the absolute resolution will depend on the velocity model accuracy as well as the P&S picking accuracies. So to optimize the absolute resolution, we need to optimize the velocity model. And so ideally what we would like is the check shot down here in the stimulation region and simply measure the velocities to each of our geophone strings. Or alternatively, we've looked at the possibility of putting a sensor here near the toe of the well, and this also gives us information as if it's for the early events, as if they're check shots. But in fact, what we're most likely to get is going to be a check shot, but with no time zero. So in this case, we will determine the P and the S velocities from the move out across the arrays, and also from the relative arrival time at each of the arrays. Now, since this is a modeling forum, I thought I should actually try and explain how the resolution modeling works. This will be the only formula I present, so please bear with it. If you look here on the diagram, if you consider this point G, this is a point where we want to evaluate the resolution. So for our model, we can measure we can calculate the P and S time from the point to any of our sensors in the network. Right. So that's the first step in the modeling. And because for real data, we don't know the origin time of the event, our reference time is actually the average of the arrival times. So the equivalent for our resolution model here is shown here as T average. And so to calculate T average, we sum up the P and S times to each of our sensors, and then just take the average, which is 2 times the number of sensors. So that gives us our reference time. And so our data, if you like, for the modeling, delta T, is the difference between our model time for each sensor and the average time. So that gives us our data for point G. And then to test how far away from point G an event could be located, we estimate again the error between the arrival times for these two different points. So we take this test point here, which is shown as the blue bob, and we go through the same process, and we calculate T average for the test point, and we can calculate the P and the S arrival times from the test point to each of our sensors. So now what we can calculate is what I call delta T error here. And this is simply the difference in time between our delta T for our grid point and the delta T for the test point. And what we do is for successively larger cubes, we search all the faces of the cubes, trying to find the point for which RG is the largest and for which the errors do not exceed our picking errors. Right? So we move as far away as possible from our grid point within the constraint that we cannot exceed our estimate of the picking errors. Right? So that tells us what our accuracy is for the picking errors at point G. And we repeat that process for our orthogonal sections, vertical sections, north, south, east, west, and a horizontal section. So that's how I generated the contour plots here. So for each point in this contour plot, I've estimated the resolution as I've attempted to describe by this method. Okay, next, the sensitivity modeling. So here we followed the method of Freudenrich et al. In 2012, and what they describe as a method for estimating the minimum detectable magnitude. So this is the minimum magnitude you could expect to detect for a given sensor, and they provide a method for both P and S waves. Here I've estimated the minimum magnitudes using the S waves because that's what we tend to do in reality. Because the signal to noise of the S wave is better. And the other assumption in it is that we're using the average S wave source radiation pattern over the focal sphere. So the parameters we're using for estimating the sensitivities then are shown here with Q is 350. And these have been derived by fitting the moment magnitude values, which were calculated by Schlumberger from the pilot hole monitoring in 2019, with the minimum detectable magnitudes calculated using this method of Freudenrich. So these are the parameters we used in the modeling. There are also a couple of parameters that we take from just sort of experience, and this is the signal to noise ratio for the shear wave, which for the smallest event we might normally expect to locate would be around 3. and the background noise level, which is for a good quiet acquisition system, such as we're planning to use, would be around 0.01 microns per second. So what I've done is I've calculated the minimum detectable magnitudes for the most distant sensor. So this is saying that this is the magnitude we could expect to detect over the whole of the array. And so here for the same sections as for the resolution modeling, I've calculated the sensitivity. In this case, the most distant sensor is at the top of 5632. So actually this one here. All right. So what this is showing us is that for our primary network, we can expect to see events of around -2.1 to -2.2 at the tau of 16A. So now if we look at the long-term network, as I say, when we finish monitoring the stimulation, the 3 geophone strings will be withdrawn and replaced by these 2-level strings. These 2-level strings have actually got higher temperature specifications. They are analog tools, similar actual sensors within the tools, but in this case they're clamped by a spring-loaded time release arm. And I'll show you that arm in the next slide. So we will deploy these tools again according to the temperatures that they can withstand, and also the temperature limit of the wire line. So an interesting consequence of the higher temperature spec of these tools is that here in 5632 we have the possibility of deploying a tool beneath the tau of 16A, so beneath the stimulation zone. So this is actually quite good from the perspective of getting good depth errors on the event locations. So these are the tools we're proposing to use for the long-term monitoring. It's as the name of PSS, it's the acronym that Avalon have for these tools. They're 2-level strings, and the separation between the levels will be determined from the temperatures. The time release arm is shown here. So this is it in its closed position. And what happens is it's held in by a pin, and the pin is made of a special material which degrades in water over time and then releases the arm to clamp against the borehole wall. And the time it takes for this degradation to take place can be controlled by machining the pin to be stronger or less strong in the first place. So the 2 models of this tool, or of the clamping arm, this is a 7.5-inch model, and this is a smaller model for a smaller diameter hole, such as we will have. The 2 versions of the tool specify for 225 centigrade or 260 centigrade. They don't have active cooling. They are relatively simple and low-cost analog tools. What they do have, though, is a times 500 amplifier downhole, and this is essential to provide good signal-to-noise ratio over a standard 7-conductor wire line. These wire lines don't have very good sort of electronic performance. So those are the tools we'll be deploying. And here they are shown on the temperature profiles. And as I was saying, the tool here in 56, and the upper tool will be at around 7,400 feet, which is at about 195 centigrade. But the deeper tool can be deployed quite a lot deeper here, right at the bottom of the hole, where we should be around 229 centigrade. And again, here in 7832B, these tools, because they have higher temperature specs, we'll be able to deploy them at greater depth than the strings. So this deeper of the 2 tools could be deployed at up to 8,200 feet, according to this sort of projection of the temperature profile. As this is the temperature at which we expect to reach the wireline temperature limit, which is 246 centigrade. So in fact, although the tools have a 260 centigrade spec, we can't deploy them at that temperature because of the wireline. So here I've shown the resolution for the long-term network, which are the green spheres again. And this is for the same sections as we showed before for the primary network. And you can see the distribution of the resolution is not as consistent as we had for our nice triangular network with the tools at roughly the same depth of the primary network. But it's been calculated for the same velocity model and the same picking accuracies. And just for comparison, here is the resolution for the primary network. And in fact, because these tools are deeper, in this sort of area here, you can see we actually get slightly better resolution than for the primary network, but it's less consistent. So what this shows actually is that the resolution is constrained by the geometry. It's not the number of tools in the strings isn't really the key factor here, it's the geometry. So here that was the sensitivity we are estimating for the long-term network. And because the tools are slightly deeper than the strings will be for the primary network, we can expect to have slightly greater sensitivity for the same parameters, and perhaps by 0.1 of a magnitude unit. However, I'm a bit cautious about this because this all depends on the noise floor of these analog tools. And whilst we know that the performance of the digital tools is really very good, it remains to be seen what the noise floor will be on these analog tools. Okay, so that's the two networks that we plan to deploy. I just want to say a few words also a little bit about the innovative tools we want to test. And these tools will be tested in the wells on the 7832 pad. So there's the original shallower 7832 well, which is 3,280 feet deep, and the steeper well 7832B. But what we will have here are the Silixa Carina DAS system cemented behind the casing. These systems are already installed. Obviously, for the older well, it's been there for some time. And this is another Carina system which has been cemented in recently into the new 7832B well. It doesn't go all the way to the bottom because of difficulty with the deployment. It actually goes to a depth of 3,993 feet. Also in 7832, we will have the 3-level fiber optic system, and this will be clamped with the same sort of time release arms as the long-term network. And in the wireline to this system will be a DAS cable, which is referred to as Suisse. This is just a proprietary name. So we'll have the opportunity to compare the performance of a wireline DAS directly to the Carina system cemented behind the casing. And in 7832B, we will have during the stimulation this 8-level tool as part of the primary network. As I've mentioned before, this tool is going to be at a higher temperature than the tools in the other two monitoring holes. And this tool uses an enhancement to the active cooling function, which enables it to, or should enable it to withstand the higher temperatures. So this is another innovation we want to test. So shown here, I'll just show you some data we already have from these tools. And this is the events that were acquired during the pilot hole stimulation. So the events are down here around the bottom of the pilot hole. Shown here in green is the 12-level Schlumberger string, and behind the casing here is the carina system. And just for comparison, here is one of the largest events as it was detected on the Schlumberger string, which is a clamped accelerometer type tool. And we've got signals noise of probably greater than 200 on the P waves here. And this is the same event on the carina system. And you can see obviously the signal to noise is a lot lower, probably 2 to 2.5. So nearly a factor of 100 difference. Now, I understand from Selixa that they were anticipating better noise performance of the system, and hopefully for the next phase of the 16A stimulation, we'll see if they can improve on this noise. This is the 3-component fiber optic system from Avalon, shown here on this little trolley. So these are the 3 tool levels. So within each of these tools is a 3-component fiber optic sensor group. This tool system is really of great interest to us because it's got a 200 centigrade tool specification, and there is potential to go to higher temperatures. So this is very important for the sort of long-term high temperature monitoring at depth that we're looking for the Ozone project. And we're looking forward to good reliability from this type of system because it's got no downhole electronics. It uses metal to metal seal, so there's no elastomers degrade over time, will be affected by gas. It's got this single shot type clamping arm, which again it's got no motor driving it, so no electronics. And say it's 3-component fiber optic sensor groups. So in principle, this should have very good high temperature reliability. So it's an important test for us to be making. One limitation of the system at present is that the tools, the string has to be made up in the workshop. Once it's in the field, you can't reconfigure it, you can't change the separation between the tools, and you can't repair it. It is what it is. And so you take the string into the field and you attach it to the wire line. And as I mentioned, there's also DAS in the wire line. So that's the fiber optic tool system. We have performed a preliminary test of it at the Dretto. And for this test, we use sparker shots shown here by the black pluses. And they're shooting here I'm just showing one of the groups of the fiber optic tool. And so, we've got pretty good signal to noise, a nice clean first arrival on each of the shot depths. So this is the same receiver tool for successive shot depths going down the hole. Right. There is actually quite a bit of noise, background noise, and this is being generated in the interrogator. So there's some work being done now to try and improve on that. So that's the fiber optic tool system. And I think at this point, I hand over to Falko. So thank you very much for listening into that part of the presentation on the resolution and sensitivity. Thank you. Over to you, Falko.
Thank you, Ben. So let me see if I can take over and share the presentation from my monitor. Are you seeing my screen now? Can you hear me?
We can see it and we can hear you.
Perfect. So in the previous slides from Ben, you have seen that we go through a lot of effort to monitor seismicity. And the reason is, why are we doing this? And Of course, we do this to have the best understanding of the processes that happen underground, but also, of course, to stay safe and also not to risk the entire project because the induced seismicities grows too large. Yeah? So in the following, I would like to give some real examples of projects that failed because of the seismic risk that was not considered or underestimated. And I see these mistakes repeatedly and in many projects. And this is why I put as the first bullet point for mitigation, learn from previous mistakes and make it better. So let's have a look at the first commercial EGS project in Basel. What can we learn from it? What are the lessons learned? So maybe you're familiar with the Basel project. Was the first EGS, commercial EGS project. And regarding the seismic risk, it was not really considered an issue. It was the first, so one really didn't know what to expect. And yes, the information was there, and the effort was about 2 pages for instruction. But after the stimulation continued, they got a local magnitude 3.4, and they had to stop the project. And when they had this magnitude 3.4, they did a comprehensive risk study after the project. First lesson learned basically is do a risk study first. It may seem obvious, but it's not. Some projects start without a risk study. So another point you can learn from projects is that they inject into large faults. I list 3 examples in time chronological order. So we had another project in St. Gallen where they were targeting a fault because just the permeability is better, and they were thinking this is they would be more successful with the geothermal project here. And then you can see this here on the right side, a sketch. So black is well, and in red you see the faults they're targeting. And they drilled into a limestone molasse base, but below they have a permacarboniferous troughs, and these green arrows, they denote gas, and I will come to this later on. So a second example of projects that stimulated a fault willingly or unwillingly is Vorhang. So there they got a magnitude 5.5 because they're not directly stimulated probably in the fault zone, but to the both sides of the fault, and they had losses that definitely went in. This project, of course, had to be aborted after the magnitude 5.5. This project had also no risk at the beginning. And the latest example is a project near Strasbourg in France, where they injected into a fault system, actually, or a fault zone that is more than 10 kilometers long. Just recently, they had a magnitude 3.9. So they also had to abort the project. So first mitigation, change the concept. So if these concepts don't work, come up with and here in this slide, I want to show kind of the lessons learned from Basel. And in this sketch here to the left, you see the Basel system. So you have 2 vertical wells, and you inject in one and try to produce from the other. And one thing what happened actually was when they inject into the open hole, the fluid went right underneath the casing shoe. So all the expensive well, the deep part was actually wasted. And so this is the risk when you do a single stimulation, a large one. Of course, you want to have a large area for a heat exchanger, but it can happen that you have a hydraulic shortcut, or you're wasting the depth of your well or your full potential. And also because you're stimulating a large area means you have a potential large rupture area. So you could end up with a large magnitude geothermal project. So what can you change? First of all, you can change the area you stimulate, and you can do multiple. So this is basically adapted from the shale gas multi-stage stimulation concept. So you split your large area in several smaller areas. This has several advantages. If you have a shortcut, you can seal off a segment, work with the other segments, and the area you stimulate is actually smaller. So this is a potential less rupture area, and might result with smaller magnitude. And this is also a reason why we joined Forge, because the concepts are very similar. This is a concept we plan here in Switzerland. Ben mentioned it, that's Ozone project. And so Forge has a similar concept. And this project currently we do in Switzerland is blocked for political reasons. So we went into the research lab. Ben mentioned the Bedretto lab in Switzerland. This is a lab which is 1.5 kilometers inside there. So it has a 1.5 kilometers rock above in the Swiss mountains, and just this multi-stage concept there. So this is kind of a slide that summarizes what we did there, just to give you an impression. To the top left, you see the tools that we're also going to use in Forge. And to the right, you see kind of the multi-stage concept. So what you see here is a multi-packer. You have rubber elements that can seal a certain segment, and you have a sliding sleeve that you can open or close. And so you can communicate with the interval or close it off. And in the middle, this is kind of the final result, just as a summary. You see two wells, they're about 100 meters apart, and different colors and symbols. You see the simulation of the different stages. And there, the seismic clouds are between 30 and 50 meters in diameter. So that actually was the first proof of concept of the multi-stage. And actually, we're pretty successful, and we're still alive. So our mitigation measures work in this case. So I showed you that by changing the concept, you can mitigate your risk, but also you have different tools. Probably the most you're familiar with is the traffic light system. It was already mentioned. So what is a traffic light system? Basically, it's a threshold-based system. You can either have a magnitude threshold or a ground motion threshold. And if you exceed a certain threshold, you have action items. So for example, if you reach a certain magnitude, you can stop pumping, you can bleed off, and then you usually have an alarming procedure that you follow when you trigger this threshold. So this is an example I took from a poster from a Schatzalp workshop for the Korean project. So what's the experience with the traffic light system so far? So all these projects I mentioned, they had traffic light systems, but why did they get these magnitudes still? And for example, let's have a look at St. Gallen. They had a traffic light system in place, but you remember the picture I showed with the green arrows? While they were testing the well or measuring inside the well, they had a gas kick. So what you do to cure a gas kick or to avoid a blowout, you have to inject water or heavy mud. And so they inject mud, and the traffic light told them, look, you're exceeding your thresholds, but they couldn't stop. So they had to inject more, and consequently, they had this large earthquake. So in this case, they had traffic light system, but they could not follow their procedures. In Basel, they also had a traffic light, and probably was the first of its kind after an example from Ecuador. But here they had not known about the trailing effect. So what is the trailing effect? It's also called post-injection seismicity, and I show this to the bottom right. So here you see various geothermal projects and the magnitude they encountered during stimulation. In red, you see that the largest magnitude tends to happen after the stimulation. In this case, this was not known, so the thresholds were pretty high. This was a problem not known, but now you know, and now you can act accordingly. And another thing, it's also a design issue with the action plan. There are projects that have no storage for bleed-off. So what you usually have when the first action item in these traffic light systems is to do a bleed-off, but where to put the volume that comes out of the well. So there were projects that just they forgot about the storage. So they had to make a choice between pollution or potential pollution and not following the traffic light action scheme. So basically they kept the well shut in for a while until they could deal with the outflow. So the experience so far is that yes, the traffic light system is meaningful, but often there were design flaws, and the traffic light systems did not capture all the possible scenarios. From this, we can learn now and make it better. So what can we do? So first of all, a lesson learned from Basel is consider post-injection effects. So in this case, be more conservative. So know about, have an estimate about your post-injection seismicity and subtract the threshold for your traffic light. Another lesson learned, what I showed, is make sure you follow your action plan. Think about what can go wrong, and if you can still do and follow your action plan. What I didn't talk about is Also an issue, was an issue, some geothermal projects, and here just call it get your magnitude straight. So usually you have an authority that communicates the official magnitude, and then you have the operator that has his magnitude. So this can be different magnitudes like mobile magnitude, local magnitude, or just the way it is measured, or a different network that will produce different magnitudes. So it can happen that the authority thinks you exceeded the threshold, but the operator continues injecting because he thinks he's safe, because he's using his magnitude. So you have to make sure that you have harmonized your magnitude, that you're measuring similar things. And this can be done by a stimulation test. It's also a mitigation measure, a pretty important one, actually, most important. Don't start full. Just do a little bit and then make sure that everything's working and that you can calibrate your magnitudes and get an idea about the seismic response of your system. So here I put a slide from Shapiro et al. This is about the Seismogenic Index. Many may be familiar with it. It's basically a proxy of the seismic response to injection, I would call it, just in a sloppy manner. And what it does is, what you see here is on the x-axis is the time, and you see these lines are constant in time, more or less. So when you're here in the project, you can already see where this is going, right? So you just need to inject a little bit, and then you can already kind of project what is going to happen. And this enables you to think about failure probabilities of your traffic light. So here we said, yeah, we want to be conservative and we subtract the threshold, but tells you that you're not still exceeding a threshold. And that, for example, what happens, let's say your red is at magnitude 2, what's the probability to get a magnitude 4? It can happen, we see it can happen, but with the stimulation test, you can give it a probability, and then you can know more about the future of your system. And also these stimulation tests and forecast abilities, they lead to a whole new concept of traffic light. That's what we call the adaptive traffic light system, that's what Ben mentioned before. So now instead of reacting, so traffic light is always something happens, you react, you can be proactive. So you can forecast and act actually before something is happening. And this is what we want to apply in Forge. So adaptive traffic light systems are still, it's not a product you can buy, but it's still under development, and many people are working on this. And this is what we will do in Forge, for example. So in Forge, we will real-time calculation of the p-value, exactly to do this, to forecast exceedance probabilities. This can be a simple statistic extrapolation, but it also can be coupled with hydraulic models, and you can add many layers of complexity here. And then what also is part of the adaptive traffic light system is some real-time clustering, cross-correlation to existing events, just to have a better picture in real time. Usually you do this after a project, and it takes several months, but we do quite a tremendous effort that we can do this in real time. And last but not least, the real-time relative location. So this is also what I did not mention so far. This is also an analysis of traffic light systems. What is not there is what if you leave your comfort or your confined zone. It can happen that suddenly seismicity pops up somewhere else, and then you have to be really sure that it's there. It's not a matter of location uncertainty, but based on your real-time location, on your advanced location methods, you're sure it's there, and it has a rather small location uncertainty. And what I mean by this, you can see this applied actually on the next slide. So here I show a processing work of Ben Dyer. So this has been done after Basel, but now we want to do it in real time. And what you see is depth slices from top to bottom through the reservoir. And so now I go 100 meters deeper, and here you see the clustering and what it can do. And here you see the different clusters in different colors, and you see that they already align very well. So this is very precise, and you can see, okay, maybe I'm stimulating a structure here. So I go deeper, and here I see that there's a second arm developing. So actually, I'm not even stimulating one fault, but actually a cross-section of a fault. There's two faults here. I go deeper, and you see this very nice alignment across feature here. And to continue, so to be fair, not everything can be clustered and cross-correlated. So in gray, you see the unclustered events. And in black and red colors, you see the post-injection seismicity. And this is the overall picture of Basel. So this is how it could look like, or this is what we aimed in Forge in real time. And so far, our adaptive traffic light is rather simple. As I said, it's simplest thing is just an extrapolation of the magnitude frequency distribution. But the overall concept of the adaptive traffic light system is there for years, and we're adding on complexity and more details. And this is kind of the ultimate target, which we do in collaboration with the Swiss Seismological Service. It's part of the DEEP project. Some of you might work on, and this is what is planned. Basically, you take all this data and you can feed this into a seismicity forecast model. You can do a real-time performance assessment as the project progresses. You may have different forecast models which you can weight based on the quality, what they forecast. And you get a seismic catalog, and you can do and update your risk study in real time. And if you want, you can add a decision module and a feedback loop to your flow control. So all these things actually enable you to plan your stimulation better. That's the overall goal. And with this, actually, I want to conclude just the acknowledgements. We're grateful for the financial funding for this, for the DOE and for the Swiss Federation Office of Energy. And I hope to see you soon in the States. This I'm finished. Thank you very much.
So this is Ben. I hope you can all hear me again. Does anybody, or would anybody like to ask any questions?
Everybody's silent.
Greetings, Ben. This is Jonathan Aho Franklin from Rice. It was really interesting talk on all the different borehole instrumentation you guys are planning. I was curious a little bit more about the wireline DAS deployment, and in particular what interrogator you're using, and any comments on the cable, what you're planning for that, since we are hoping to have some DAS cables and other wells, which might make for good comparison.
Yeah, this is a system from Avalon. Avalon, they call it Suisse. I think it's a Phoebus interrogator. I've got to admit, you've caught me there. I don't really know what it is, but I think that's what it is, Phoebus. It's the first time we'll have seen it, actually. Though we had the 3-component fiber optic tool in Bedretto, we didn't actually have an opportunity there to test the fiber optic in the wireline because it just wasn't deep enough. So we're going to be pretty interested to see how it performs as well. Can I ask you, where are you planning to deploy DAS at Forge?
It'll likely be in the 16B well behind casing and the 16A well possibly on wireline, but this is still under negotiation, so TBD.
Right. I think one of the difficulties is going to be that these things have got to be defined before we'll learn anything in the next simulation, because the 16B well planning will be going on and maybe fixed by the time we have any results from the stimulation of 16A.
Yeah, I mean, it's there's still a lot of stuff to be worked out, so I'm looking forward to talking to you guys a little bit more. Are you planning on recording on both the going back to the DAS, on both the wireline cable and the stuff cemented behind casing, because that might be an interesting comparison as well. Just because intervention is is a little bit easier in some situations.
Yeah, that's right. We will record both of the behind casing DAS, which Alexa will acquire that data, and we will acquire the wireline data. And we are actually working on being able to integrate the data from these different systems. So this is a bit of a challenge, but that's our ambition, to at least be able to integrate part of the DAS data. I mean, there's going to be a large volume of it, but if we can extract a certain amount of it, we can at least do some quality control in real time, so that we can see that that they're all time synced, and if there are any major problems, we have a chance to deal with them. So it's a bit of a challenge, but I think because we'll have the acquisition cabin on the pad at 7832, where the DAS will be acquired, it's probably a little easier than shipping DAS data from the further offset wells.
Yeah,
so that's
sounds great. Really looking forward to talking to your team in the future. I know there are a couple of other teams who are acquiring DAS data too, so we should all meet up in not too distant future.
I think that would be an excellent idea. Yes, thank you. I think from our perspective, you'll either have to meet on Zoom or something, or your government will have to relent a little bit and now travel to you to come and see you.
For sure. I think Zoom's in our future for the not too, at least for a while.
Yeah. Okay. Thank you for the question.
This is Bonju. I have a question. So have you done any modeling to predict the seismicity during the stimulation?
Sorry, you got a bit poppy there, Ben. To predict the what during stimulation?
Yeah, so predict the seismicity during the stimulation. Like
I can try to answer. So you've seen the slide from the Pedretto lab, and this is where we tried this out. And there the magnitudes and time was fed in real time together with the hydraulic data to various algorithms that forecasted seismicity. And from this, we got a feedback if we're safe, so to say. So we got an exceedance probability for a certain magnitude, and this was part of the traffic light system. So before I said that the threshold for the traffic light system is magnitude or ground motion, but in this case, we also had a exceedance probability for a certain magnitude. And as I said, these forecasting can be very simple. They can be pure statistical, but it can be also physics-based hydraulic models. And I think what we plan is, or what is in discussion, is that you have up to 12 or 14 models that could compete for the best forecast.
Okay. So you have the model ready, but you just need the data, right, to put in.
Yes, so we have at least 2 models ready, and we see what we can do in the following.
Okay, thank you.
So I wanted to make sure we take the opportunity to thank Ben and Falko for their presentation. This is Chris Panko from the Forge team. So we appreciate you coming and giving this presentation. I just wanted to make sure we had a chance to say thank you, but not to shut off questions if there's more questions out there.
It looks like that's all of it we've got for questions. Obviously, if there's anything anybody thinks of later, then please just send a message to myself or Falko as appropriate, and we'll get back to you. So unless there's anything from anybody else at the last moment, I think I'll say thank you very much for joining the meeting today again, and look forward to meeting some or all of you in the future. Thank you.
Thank you.